Hey, good evening, everybody. We've got a pretty busy weather day here, very dynamic weather patterns, and you saw 160 knot cirrus overhead just streaking on by, and we're going to dig in and look at that a little bit closer with some special tools that we have not done on this WEBCAST before. So I'm going to set you up with the big picture here. This is the 300 millibar analysis. So this is going to be up at about 30,000 feet. And as you might guess, the red coloring is ice attacks. So this is going to be roughly about 110 knots, and the shading is off on the bottom here. And yeah, thanks to Pivotal Weather for these charts, they're working out pretty good. So you can see we've got two main cores here. We've got the polar front jet up to the north, and then you see this other band here, and it's got kind of an anticyclonic twist to it, and that's a subtropical jet. And we sometimes refer to that as STJ. And the north one, I don't know if that's showing up. Let me check over here. Yeah, I think that's working. We go PFJ on that one. Okay, let me check over on chat, make sure the audio is working. And looks like no problems there, or the chat would be filled up with complaints, I'm sure. So yeah, let's look at the surface chart. And before I do that, you should know by now, if you've been watching this for a while, when we have a big old trough, that usually means a cold air mass. And when we have large-scale ridges, that means a warm air mass. So we're going to expect to find the surface front kind of in the middle. So this is going to be our surface chart for right now. It's actually the 6-hour GFS, but it's going to be pretty much right on the nose. And this is thickness, so we're seeing an average of the temperature in the lowest 5 kilometers or so, up to about 18,000 feet. So we see the very strong thickness gradient through here. So obviously we've got a front down to the south, maybe running something like that. And it gets a little more indeterminate as we go up north towards the Great Lakes. So I'm going to call that probably an occluded front. And we could find a warm front anywhere in between. I'm probably going to go with this, since the main precip area here looks to be the most baroclinic. And I remember this from last night. We were looking at this to be the triple point here. And that is a triple point, by the way. That's the intersection of the warm front and the cold front, and anything north of a triple point is going to be an occlusion. And the cold air mass does check out. Got a lot of cold air up to the north. So here's what we're going to do. And we're going to look at the 300 millibar chart. We're going to do a cross-section like that. We don't too often do like that, go longitudinally along the jet. Usually we go across it. So this is what we're going to do. The section I'm going to pick, let's go from south of New Orleans to, I guess, Yankton, South Dakota, maybe one of the native reservations up there. I'm going to use a tool called wind grids. And here's what I'm going to do. I'm going to set this up. This is probably going to be a tiny bit hard to read, but we will get through this. So I'm going to set up the cross section, and there's a map window for this. So south of New Orleans up to the tribal smoke shop on, I don't know, 40 in South Dakota. And we got that set up. And you can see that overlay show up there very briefly. Okay, so here's what we'll do. I'm going to plot the temperature field. Maybe I'll do that a little bit differently so it's not so messy. And I'm going to add the grid for the heights and everything. I know this is a little hard to read. I can't really stream any better than a 480p right now on these lines here, so this is going to have to do. So anyway, what we're looking at here, this is going to be Louisiana, or this is just off the Louisiana coast. This is Louisiana. This is Arkansas, Kansas, and then we get up to the old tribal smoke shop up off to the left there. So what does this tell us? Well, we're looking at temperature. Here's 900 millibars, 800, 700, 600, 500. That's going to be up 18,000 feet. 400, 300. This is 30,000 feet. And then up at the very top, that's going to be up at 50,000. And this obviously is the ground. So this is showing us that the temperatures do fall off with height, as we would expect. We can see that the temperatures are packed a little close together in some areas. Other areas they're not. Now when temperatures fall very quickly with height, we call that a very steep lapse rate. And that's happening in this area here, in the upper levels over Louisiana. So this is very steep lapse rates, so that's going to be a area of high static instability. So if we have enough moisture present, that'll be a good area for thunderstorms. Where they're far apart, here, this is going to be stable or an inversion. In this case, this is the stratosphere, which is very stable. But this chart is very difficult to use by itself. We almost never use temperature with a cross-section like this. So how would you find a front with this? Okay, I mean, we can see that it cools off as we go to the north, but, you know, we might be able to find a little change in the slope here of the temperature. But let me show you a trick. We're going to use potential temperature. That's where any temperature reading we take in the atmosphere, that's measured according to what the temperature would be if we dropped it to 1,000 millibars, which is around the surface, if we dropped it adiabatically. Okay, so check this out. Okay, so this is a little different. Let me add the labels. Okay, so what we're actually seeing here, we can see this is actually a lot easier to read, and when we have the lines grouped together, that can indicate a frontal boundary. So we can actually outline the front pretty easily like that. And up above that, we can see the tropopause and the stratosphere. All of this up here is the stratosphere, all the way up to the very top, which is about 50,000 feet. So this is pretty cool. We can see how the tropopause gets lower out in Nebraska and Iowa, and it's a lot higher up at about 45,000 feet over Louisiana. And there's a couple of very important things. You see where the slope is very strong and there's this packing. That's a very strong thermal gradient, and there's always going to be a response aloft over these areas. And that response is very strong wind speeds. And that's actually what's causing the jet right there. And you see this packing here? That's responsible for the subtropical jet. Let me see if I can add that on real quick. In fact, give me a second. I'm going to have to pull up this command by doing this deal here. Theta contour interval 5. Add. Okay, let's see if this comes up right. Yeah, okay, you see that? Now I've added, let me add the grid on. I've added the wind, all the winds above 70 knots in yellow. And you can see the jet core right there. And it's kind of like a split core. You see there's some grouping of it very concentrated in this area, and there's another group right around here. So this is the coupling of the jet. And you can see it's overlying the red lines, which is the strong temperature gradient right in here. And it's also overlying the the frontal zones. And you can tell that there's not very much slope as we get lower in the atmosphere over Louisiana and Arkansas. So this is actually kind of an elevated front, believe it or not. So these cross sections are a pretty cool way of looking at stuff. Wind grids takes a lot of time getting used to, but if you want a quick cross section, you can go to College DuPage, weather.cod.edu, and that's under Weather Analysis Tools. That's going to be under Analysis Data, under Cross-Sectional Analysis right here. And they've got some predefined cross sections, so you don't get a whole lot of flexibility, but you can do similar charts to what you see here. Okay, let me look over on chat because I kind of covered a lot right there. The jet is around 35 to 40,000. Yeah, let me go back to that chart and show you how high everything is. I know this is very hard to read because I'm having to squash this window down. Let me see if I can try this again a little bit better. Yeah, this is a little easier to read. 1,000 millibars, 900, 800, 7, 6, 500, 400, 300, 200. So this core right here is up at let's see, lost track again, 98765. Okay, this is up at about 300 millibars. That's up at about 30,000 feet. And the subtropical jet, as we'd expect, is up higher. And this is up at about 40,000 feet. And this is actually some of the cloud material you were seeing in this area, in this frontal zone underneath the jet. When we opened the WeatherCast, you were looking at some of that cloud material. Now I'll show you one other thing. Vertical shear is a very good way of finding turbulence, clear air turbulence. And all you're doing is looking for the tightest packing in the vertical of wind, which is yellow here. So that's going to be a very possible area for turbulence. And that's pretty much right over East Texas. And then there's this other area here a little bit lower. See right there, that's over Oklahoma. So if you're flying over Oklahoma, you're getting bumped around a little bit. That's because you're underneath the jet core. And it could be actually a little bit better to ascend and go a little bit higher. And the pilots sometimes do that. They'll call up the center, air traffic control center. They'll request a couple thousand feet higher and see if they can get a smoother ride up there. Turbulence forecast, let's see, I've got a graphic for that. Yeah, here it is. This is the turbulence forecast right now. This is numerically generated. Let's see, max combined. And we did our cross-section like this, and we picked out turbulence there and turbulence there. Now let me take this down to 23,000. Yeah, there's that polar front jet turbulence that I showed you. That area right there, this is what we saw right here. And then if we go up higher, up to, let me move this so you can read the legend. See, I'm going to go up higher to 29, 31, 33, 35, 37. Now we're picking up a band a little bit further to the south. So that's going to be the other jet core right here. Okay, so that's kind of like some just nuts and bolts I wanted to show you. And okay, yeah, no problems there. So let's check out the, let's go back to the current conditions. Okay, so we've had a front kind of push through Texas. I haven't looked at exactly where that is on the surface chart. We might want to go ahead and do that. Here's the map for Texas and Arkansas, Oklahoma. And you can see that at this hour, things are pretty mild all across this area. It's pretty hard to find exactly where that front is. It brought some milder air into Texas, upper 50s here. Looks like the cooler air is actually up in Oklahoma, so maybe we're looking at maybe a front through here. No, actually here it is. Okay, so that pushed all the way to Louisiana and to the Texas coast. Where is it up at 925? This is the 925 millibar temperatures. Don't really find it too well. The strongest gradient is way up here in Oklahoma, so maybe the front has kind of lagged a little bit, maybe. 850, well, actually 850 is showing it kind of, yeah, in East Texas right there. But then you'll notice it kind of shifts further north as you go up to 700 millibars. So there it is through the Dallas area, and we go up higher to 500 millibars. It's up at the Red River. This is kind of what we call stacking of a frontal surface. We go up higher and higher, and we find it tilts towards the warm air or towards the cold air. And one interesting thing here is you can see there's a lot of cold air at 500 millibars, 18,000 feet, overlying Oklahoma, not so much over Dallas. So what does that look like on the soundings? These are the soundings from the last hour. Fort Worth is looking like this. You can see, man, we've got very steep lapse rates up to about 10,000 feet. That's what we call dry adiabatic. And that kind of profile is very good at raising dust and also ducting strong upper-level winds to the surface. But up above that, you see kind of this layer of warmer air. But if we go north to Oklahoma City, it's not so warm in the mid-levels. It's a lot cooler. So much deeper layer of high static instability there in Oklahoma. And you can see the tropopause is a lot lower, down at about 30,000. Okay, so that's kind of what's going on there. Hopefully I didn't lose any of you guys. If you have any questions, you can post it and I'll try to catch it in the chat. But I'm going to go ahead and move forward and get us toward our forecast here. This is some of the clouds you were seeing there on the time lapse. Oh yeah, we also have some storms in Alabama. This is the water vapor imagery, and you can see a lot of strong subsidence in Illinois, in Arkansas right there, showing up very dark, so that indicates very dry, possibly warm conditions there. And out ahead of it, a lot of lift, and if we go underneath the clouds, look at the radar, we got a squall line going all the way from about Cincinnati down to Nashville, down to central Alabama right there. Is that causing tornadoes or anything like that? I don't really know. We can check out the Weather Service warnings page. Looks pretty benign here. Yeah, they got a lot of wind advisories and one tornado watch for southern Mississippi. So why is that? Why don't we have like a widespread severe warnings? Well, this is the instability profile. This is the most unstable instability, or the most unstable cape. Let me show you how to get that. That's on the SPC experimental analysis page. Let me see if that's showing up. Okay, yeah, there it is, spc.noaa.gov/exper/mesoanalysis, and you're going to go to thermodynamics and go to most unstable, Now you can use surface-based, but that uses a lot of assumptions, and surface heating is very important for that. You can use mixed layer, but that may not. What I'm looking for here is like the most unstable layer, because if we have elevated convection, which is very possible, that's going to be very good at catching that elevated instability. So what values are we seeing here? We're seeing 500 joules per kilogram, and then 1,000 over Louisiana. 1,000 is kind of like the threshold value for thunderstorms. You can get them with 500, but that's very, very iffy. So these are all developing in 300s and 200s, which is barely adequate for thunderstorm activity. So can we get tornadoes? Well, one thing we can look at is the shear. We can look at the storm relative helicity, surface through 1 kilometer, because even with weak thunderstorms, you can get tornadoes. That happens sometimes. And you can see the shear is actually cranked up pretty high here. We've got shear values of 500, 600, 700. These are actually storm relative helicity values here. And anything over 200 to 300 is getting into the range where you need to keep an eye on things. And these high SRH values are being caused by strong shear in the lowest 0 through 1 kilometer. So in other words, at the surface you might have weak winds, and then as you go slightly higher, they increase and turn. And that's very effective at generating storm relative helicity. And I'll show you this neat little diagram here. Let's go back and look at CAPE, most unstable CAPE. This is a box and whiskers diagram. I think I got a better version here. This is generated by SPC and the work of Rich Thompson and Roger Edwards. Those guys are pretty good at digging some of this data out, and they've actually got a page called Explanation of SPC Severe Weather Parameters. That's a good one to go to. And there's the link for that. You can read that back on the playback later on if you need to, or you can Google this. But they've got all these predictors for different types of shear and instability. And the one I want to show you is CAPE. This is purely instability. Moisture and steep lapse rates, basically. And what you're seeing here is a box and whiskers diagram. Values between here and there is between the 25 and 75% range. This is between the 10% and 90% range here. So what this is showing us is that for significant tornadoes, about half of the cases we had were associated with CAPEs of about 2,200 to 4,000. In other words, the median was about 3,000 joules per kilogram. So that's how much CAPE we really need to see to support significant tornadoes. For weak ones, kind of a bottom limit on 75% of the cases is going to be about 1,500, and then the bottom limit for down here, only 10% of the cases had less than 1,200 joules per kilogram. So these are the values we have today in Mississippi. So this is way down at the bottom edge. But we can still squeak out tornadoes because of the importance of CAPE. This is a diagram that plots CAPE on the x-axis with helicity on the y-axis. And you can see that today we have values way up about 400, 600, 800. And this shows us that we do have tornadic cases that sometimes develop when there's very weak instability, but very strong helicity. So basically, either a lot of storm relative helicity is good, or a lot of CAPE is good, one or the other. And this is kind of like the basis for the EHI index here. So they found that values of EHI 1 to 2 favor tornadoes. But this is kind of like a very strange area here. There are a lot of outliers where there's EHIs below 1 because helicity is so efficient at cranking up rotation in a thunderstorm or even a shower. Okay, so that's what I wanted to cover there. That explains why there's not a whole lot going on in Alabama, but there's still a little bit of potential for a few isolated tornadoes. So that could still happen in that squall line. So we're 27 minutes in, so we better get on to the forecast here. Let me pull up my forecast panel. We're going to look at thickness. See if I can find it here. There we go. Okay, so we're going to go into tomorrow. Okay, so this is the sequence of charts through tomorrow. And when we do the weathercast tomorrow, we're going to see some very weak invasion of cold air into Texas and the Midwest. The front should be well to the south and along the Gulf Coast region. Still a few showers hanging out in the Gulf Coast area. And then we're going to see that triple point move all the way to New England. So let me draw that in very quickly. Now we can see that warm front right there, south of this thickness packing, and in this trough that you see right there. So this is going to be a potent area in the evening for New York City, Boston, New England. And then the occluded front's going to go like that. But it will be a fast-moving system, and you can see it'll be out of there overnight. So then for our webcast on Wednesday, we're going to be looking at this situation here. Pretty stagnant, high pressure moving into Texas. And you can see we've got this northerly gradient going through the North Plains. Starting to get a little bit of a lee side trough developing in the North Plains. Then by Thursday, still got high pressure across Texas. However, now we're seeing some cyclogenesis out in the southern Rockies and developing that warm air advection over Texas. Then by Friday, we get the combination of warm air advection and upslope as our gradient turns to the east. And there's a kind of a rule of thumb at a lot of stations in Texas when you have high humidity and an easterly gradient that you forecast stratus or fog. And this is one of those situations. So we're going to look for a lot of clouds on Friday in Texas. And with these pressure falls out in Arizona, the front is going to be kind of looking like this, just to the south. So that's going to be a potent area for development. And there it goes by Saturday. So when we do our Saturday webcast, looks like very stormy down in Mexico, rainy in Texas. There's the plateau high continuing to drive in some cold air into Colorado. And then that clears out as the system goes into the Gulf on Monday. And now we're starting to shift our attention to the northwest. See that high pressure developing there in Alberta and British Columbia. And when we see these strong fronts moving through the northern Rockies like this into the Great Basin area, usually those are very deep systems. Give me just a sec. Okay, I'm back here. Just had to clear my throat a little bit. Okay, running forward, what's going to happen with this big cold air mass? This is probably going to be pretty deep, and we see 504 decameter thicknesses coming in next week. Going into Tuesday, for our webcast on Tuesday, About a week from now, we're going to have this big cold front coming into the northern plains and across the Rockies. And the fact that it's coming through this area is pretty significant. And we're already seeing that area starting to develop on Wednesday next week. So the 7th looking like this. And we see things coming together in Texas for possibly wintry weather in some areas on Thursday. So high pressure like this, and you can see we've got that strong east gradient right here. Probably strong isentropic lift as we have mid-level moisture riding on top of this. And things get even more interesting up to the northwest. So you see that right there. Things are getting very dynamic up there in Canada, and we start to see some Arctic air start to make the plunge on Saturday. Now we're getting about 300 hours out, so things are kind of getting pretty far out there. So anyway, that's the picture. High pressure coming on south. And I did look at some of the extended models. Maybe I can pull this up very quickly. Let me go over and do that. They were showing some very strong Arctic air possibly coming in mid-December. Let me see if I can bring that up. That's on the climatological model, the CFS. I normally don't pay too much attention to this except for the large-scale details. So let me bring this up to about the 19th or 20th when it was showing this. Yeah, see this right here, very strong high. This is like a 1045 millibar high coming south. Classic Arctic air outbreak signature. And they're developing some winter weather for Oklahoma. We'll see how this pans out. I've looked for some CFS verification stats on the internet, and I can't find any. So I might have to start saving these charts and see how this model does. I don't expect too much from a 500, 600 hour model, but anyway, I can at least give you our ridiculous Christmas forecast. Here's Christmas Eve, showing a high pressure. Looks like kind of a weak Arctic air outbreak pattern, cold front into Texas. This is a very cold pattern for the central and most of the country actually here, so we'll see if that pans out. But anyway, it looks like that's going to put an end to our warm weather, finally. We've been having a ladybug infestation here. I've heard they're actually Mexican bean beetles or Asian ladybugs, but they've been a problem. They've been swarming with these 70-degree temperatures, and I'm tired of them. So let me check through the chat here, and I'll say hello to everybody. It's good to see everybody, like Sue and Alexi and Michael and Mark and Sarah and Bill. Good to see you all. And hang on, here's a question here. Do you use the RayOb software? Yes, yeah, I definitely do use that. That's by John Shuchek. RayOb is more of an analysis program. So if I'm looking at very important details and I want to modify the soundings by dragging them around, RayOb is good for that. WindGrids is good for model data with soundings. And let me just show you something very quickly. I'm going to show you the Fort Worth sounding real quick and show you how the model soundings have a lot left to be desired. So I'm going to pull up the sounding for Fort Worth just real quick. Okay, so what do we see here? We see dry adiabatic lapse rates up to about 700 millibars, and then we've got this warm layer above that. So this is the actual observed data from an hour and a half ago at Fort Worth. So what did the GFS forecast? I'm going to set this on Fort Worth. And here's the forecast sounding. And we can definitely see a difference here. You can see things looked a lot more smoothed over. It's resolving a little bit of that warm layer, but you can see there's just not the detail we have on the actual observed sounding. And wind grids is going to show kind of the same thing because it's built from the same gridded data. Now, it's possible some of the mesoscale models, the non-hydrostatic models like the NMM, those might actually work a little bit better. Maybe I can pull that up very quickly to see if they're... I don't know if we get data from... I don't know if we get forecast soundings on pivotal weather from the HRRR. Yeah, it looks like we do. So let me kick this back to 20Z and see what it forecast for 0Z at Fort Worth. And let's see how this compares. 20Z for 4 hours. Okay, so here's the HRRR, High Resolution Rapid Refresh. It's the most detailed model that the US runs. It's a mesoscale model, and you can see that still it's kind of lacking a lot of the fine detail. It is picking out the warmer layer around 700 millibars, but you can see if I flip back to Fort Worth, it just doesn't have that fine-grained resolution. So it's enough to, you know, kind of pick out where the showers are going to be and roughly how intense they are, but still this is where the human element really comes in into its own, because you can actually forecast these manually out to maybe 4 or 5 hours, and you can, within that 3 to 4 hour range, you can kind of beat a lot of these models. But past that, past 6 to 12 hours, the models are better. I just hate to say. But anyway, that's just a quick thing right there. All right, let me look over, see if there's anything else. Japanese beetles. Yeah, they probably are. I'll try to show some video of that tomorrow. And let's see. I think that's probably it for me. So anyway, I appreciate you watching the webcast, and we did 39 minutes. That's pretty good there. So hopefully we'll see you tomorrow night, and we'll try to show some new stuff and try to keep things fun. Anyway, we'll see you tomorrow.